So this video is going to take you through worked solutions to the 2017 external paper for probability distributions. In the description below, I'll put the minute markers so you can skip ahead to question 1, 2, and 3. So you can go and look up exactly which one you need to see. Okay, so the first question is about a probability distribution. We're asked to use an appropriate probability distribution model for the information we're given. We are told that there's a random variable that takes values between 20 litres and 200 litres. The most likely amount of water used when taking a shower is 50 litres. So we've got very limited information here. We have a minimum amount and a maximum amount, and then a mode in the middle. When that's the only information we've got, we need to use a triangle distribution. Okay, so we can set up what that looks like, with our minimum being 20 and maximum 200, and mode somewhere here is 50. Okay, so it's a triangular distribution. We want to be able to work out the percentage of showers that use less than 50 litres of water, so that's this area here, less than 50. So we can do that using simple geometry of working out area of a triangle. We don't need to go to the complicated formula that you've got in your formula book. Because it's at the peak of the triangle, it's a little bit easier to think of this just as triangles. So remember, the total area of that probability distribution will equal 1. So that triangle is 180 wide, multiplied by the height we don't know, and divided by 2 will equal 1. This will help us to work out the height. So 180h will be 2, h will be 1 over 90. So this bit just here, that height is 190. So now we can work out the probability, which is the area of this part, which is half base times height again. Half of the base, which is 30, multiplied by the height, which is 1 over 90. And if you put that into your calculator, you get 0.167 to three significant figures, which we've been asked to show as a percentage. So we'll just turn that into 16.7%. Okay, now part 2, using an appropriate probability distribution model, so we'll stick with the same one we were just using. Calculate an estimate for the percentage of showers that use more than 40 litres of water. So the 40 goes right here, and we want this area more than 40. So the probability of x being more than 40. Now, for the purposes of what we're doing, we actually want to find out the area of this triangle and take it away from 1, because that's the triangle we can work out. So this will be 1 minus the probability that x is less than or equal to 40. So for the area of that red triangle, we're going to need to work out the height here at 40. So that will use the formula for the triangle distribution. So that looks like this. We are, of course, using the formula for when x is on the left-hand side of that mode of 50. Now, popping those numbers in, we get 1 over 135 for the height. So now we can work out the probability from above and switch back to doing that. So the area of the triangle, of the red one, will then be half times the base, which is 20, and the height we just worked out is 135. That comes to 0.074074 and so on. So then the probability that x is greater than 40 will be 1 minus 0.7407, which is equal to 92.6%. Okay, so question 1b is about GPS navigation app and comparing the actual travel time and the estimated travel time given by the GPS app. Now the situation of this isn't too important just now when we're calculating the answer to the first part. I've just put that up in the corner so we can see the next bit of the question. Suppose 15% of trips made during the study were classified as not accurate, as in, the time estimated wasn't accurate enough from the actual time that it took. If 10 trips from the study were chosen at random using an appropriate model, calculate the probability that at most 4 of the trips were classified as not accurate. Now, the appropriate model that we're going to use is a binomial one, because we can term this as accurate or not accurate and get the probability of 15% plugged into that as well. So we've got a binomial distribution. X follows a binomial distribution. We've got 10 trials and the probability of success is 0.15. We want to work out what's the probability that X is at most 4. So that means less than or equal to 4. So we can have 1, 2, 3, or 4 of those trips classified as not accurate. And you could go straight ahead and plug that into your graphics calculator. If you can't remember how to do that, there's a video on the channel about using your graphics calculator to work out binomial probabilities. You put all the details that you need, so the 10 trials, the 0.15 probability, and the X is 4 on the cumulative calculator button, and you get the answer of 0.990. Then we move to part 2, which wants us to justify why we used that binomial distribution. Now, you'll remember there is an acronym for this, which is FIST. So there were a fixed number of trials, and we need to say what that is in context, and that was that 10 trips were tested. I is for independent, which means that each trial was independent of each other. The outcome from one trip didn't affect the outcome of another trip. S is to remember that the probability of success remains constant. So in this case, that meant that the chance of an inaccurate trip always stayed at 15%. And there were always 2 outcomes. The trip was accurate or it was not. Okay, so part 3 is asking us to take a look at a possible normal distribution to model these differences with the median, the mean time being 3.5 minutes and the standard deviation 2.8 minutes of difference between the actual travel time and the estimated travel time. So first of all, take a look at a picture. We're asked to give 2 reasons. So I'm going to just look at what that model is doing first of all to see if it looks like it makes sense. So with a mean of 3.5 and a standard deviation of 2.8, we can get an idea of what that would look like. Now we know that most data lies within 3 standard deviations of the mean. So if we do some calculations on that, we can see if that seems sensible. So doing 3 times 2.8 gives us 8.4. Now 8.4 above the mean gives us the top value we should be expecting at about 11.9. And 8.4 below gives us a bottom value of minus 4.9. Now hopefully you have figured out that that gives us some warning bells straight away. We are told this is about the mean absolute difference, which means that you always take the positive value. Yet here we've got a negative. Okay, so there's reason number 1. So since this model could possibly spit out a fairly large chunk of negative answers, that's not suitable for this situation. The absolute difference in our situation between times would always be counted as a positive number. Now, for looking at reason number 2, there are a few options you can go down here. You can think about symmetry and that sort of stuff. But we also need to look at the other information we've been given, which is this bit here, this 87%. If they've given you something like that, they probably want you to use it. So let's check that, if that 87% matches what would come out on our normal distribution model. So we can do that by checking the probability. This is saying 87% of trips have absolute differences of less than 5 minutes. So we can find out what's the probability of less than 5 on our model. Now working that out on the normal distribution, again using your calculator, go check the other videos if you can't remember how to do normal distribution on your graphics calculator. That gives us 0.004, which does not match the 87% that was recorded in the study. So there's reason number 2, that the probability that's spat out by this model is not the same as what was recorded in the study. So question 2 starts off with a probability distribution for a random variable x. It's already worked out E of x for us, which is the expected value or the mean, and we are asked to calculate the variance of x, which is to do E of x squared minus that calculated value squared. Okay, so E of x squared looks like this, where we do each of the x values squared multiplied by their probability and add them together, which comes to 6.46. So the variance will be that 6.46 minus E of x squared, which was the 2.2, square that, which gives us 1.62. Part 2 wants us to compare this new variable y with x and to see if they are independent. I've copied down the variance of x from part 1, and if those two things are independent, then that will mean that the following is true. If we add together the two variances, we should get the variance of the two independent variables added together. So if we check that mathematically, you can quite clearly see that 1.62 plus 1.5376 does not equal the variance we were given of 5.5696. Therefore, x and y are not independent. Part B is talking about the average temperatures in New Zealand being modelled by a normal distribution with a mean of 17.8 and standard deviation 2.1. So before you attempt any normal distribution question, you should draw a picture of it. So we've got the mean 17.8, remember that's mu, and sigma for the standard deviation is 2.1. Okay, using this model, between what two values would you expect the middle 95% of temperatures to be? So we want the middle section here to be equal to 95%. So you go over to your graphics calculator, you're doing inverse normal so that we can find these x values at the top and the bottom. You put in that we're looking for the central area of 95%, mu is 17.8, sigma 2.1, and you'll get the probability is equal, sorry, not probability, the x values are equal to 13.68 and 21.92. So write that as a sentence, that the middle 95% will be between 13.7 and 21.9 degrees Celsius. Part 2 is pretty straightforward. Just think of something that could influence the temperatures. When we're talking about temperatures across the whole of New Zealand, the first thing that pops into mind is it's going to be very different in different regions of the country. So at the top of the North Island is going to be very different to the South Island, for example. You could also have other things like considering the different types of property that you would be looking at. So a relatively new build would have to apply building codes to it with insulation and that sort of stuff, whereas an old villa won't, and is probably going to feel cooler than an insulated home. Part 3 takes a little bit of unpacking. We've got 5 New Zealand houses selected at random, and it was found that of those 5, 4 of them had a temperature below 16 degrees, and we want to find out what's the chances of that happening and whether it was likely or not. So we've got the probability distribution from the previous question, part of the question, where it was 17.8 was the mean and standard deviation is 2.1. So now we want to work out what's the chance of just, one of those houses ending up below 16 degrees here. So we're finding out this area here. Plug that into your graphics calculator, and we get the answer of 0.19568, just from using that normal cumulative function on your graphics calculator. Now I've deliberately left that fairly long. Don't round your answers until the end because we're not quite finished. That was just the chance of one house being less than 16 degrees. But we're asked, what's the chance that if we picked 5 of these houses, 4 of them would end up like that? Now that's actually a binomial distribution. So this variable now will follow a binomial distribution where we've got 5 that we're choosing from, and the chance of just one of them hitting this category of being less than less than 16 degrees will be 0.19568. That's the probability that we just worked out there for one house going below 16. So now with that binomial distribution, we want to work out the probability of 4 or more of those houses landing in that category. So x is greater than or equal to 4. Okay, so again, turn to your graphics calculator, and that will be 1 minus the probability that x is less than or equal to 3. This bit here we can put straight into the graphics calculator. Okay, so once you pop that into your calculator, we get 1 minus 0.9938, which comes to 0.0062. And I'm just running out of a room here to do the very last bit, so I'll just make us a little box. So this is very small, so unlikely to have happened under the model described above. Question 3 gives us a Poisson distribution to work with that is modelling the number of times that people flush the toilet in an average 24-hour period. So part AI tells us to work with this Poisson distribution where x is going to follow a Poisson distribution where lambda is 4.7. Okay, now what is the probability that a person flushes the toilet less than 5 times? So x is less than or equal to 4. Because it can't be equal to 5, it's got to be strictly less than. Now you should be instantly turning to your graphics calculator to plug that straight in with no extra working required. Simply go to your Poisson menu. We're going for cumulative because it's up to and including 4, not exactly equal to 4. It's all the numbers up to there. And lambda is 4.7, and your graphics calculator will give you the answer of 0.495 if we round it up, so to 3 significant figures. Okay, part 2, give a reason why it might not be appropriate to use a Poisson distribution to shrink that down to a 4-hour period. Now remember your acronym for the conditions to meet a Poisson distribution is RIPS, so randomly, independently, probability of success remains constant, and singly, can't double up. If we reduce that to any 4-hour period, it's not really going to work throughout the day because people are less likely to use the toilet during the night, so the number of flushes might be less. So whilst you could multiply up to do, multiples of a day, that would remain proportional, but shrinking it down to 4-hour periods wouldn't remain proportional in terms of the probability and likelihood of the number of flushes you would get during those 4 hours. Okay, so this is actually similar to one of the questions we had earlier. The mean number is the expected value of x, and you do that by doing each x value multiplied by its probability and then add them all together. And it's a little long and tedious. Just be very careful putting it into your calculator, double check that you've got everything in there correctly and you come out to the same answer a couple of times, and we get 4.74. Part 2 leads on from that same table, and we want to work out, did most people flush at least 4 times? So that's the probability of it being greater than or equal to 4. So you could add up all of those probabilities in the table from 4 upwards, but it would be faster if we do it as 1 minus the probability that x was less than or equal to 3. So that's 1 minus 0 plus 0.1, and I'm just reading those values off of the table for all of the flushes from 0 up to 3. And this will give us 1 minus 0.28, which equals 0.72. Now we need to answer the question, did most people? So yes, it's more than 50%. So yes, most people in the study did flush at least 4 times in a 24-hour period. So the last part of this question is asking us to compare the original Poisson distribution that was set out to begin with, which is the black bars, and the results of the study that came out, and give 2 reasons why a Poisson distribution wasn't a good model to use. So have a look at comparisons here and think of anything, especially in the context of what we're being asked about, things that are a bit odd and don't match up very well. I would say probably the one that stands out the most is that for the 4 number of flushes, the difference is quite big between what actually happened in the study and the estimated value from the Poisson distribution. And we can put some values in our write-up of that as well, that it's actually got a difference of 8% probability on that number of flushes being 4 on the two different models. The other thing to think about is this value here at 0. So if we're thinking about the number of flushes in a 24-hour period, it's unreasonable to think that that could ever be 0 in real life. Nobody's going to not use the toilet for a whole 24 hours. So that would be another reason why the Poisson distribution wouldn't be a good model, because it does actually give a probability for there being no flushes, whereas that's unrealistic to think could actually happen. And if you want a third reason, you could also think about the fact that sometimes in one visit to the toilet, you need to flush it more than once to be able to clear everything. So that would also affect the likelihood of the number of flushes being increased, and that's not been considered on the Poisson model. That brings us to the end of the 2017 paper. All that's left to say is good luck for your own paper. Hope it comes up nice and easy for you. And if this helped you at all, do me a favor and hit subscribe.